all solid-state batteries truly the same? Or are we mixing two very different technological philosophies under one attractive buzzword? The global EV industry is currently obsessed with solid-state technology. Governments are investing billions. Automakers are promising vehicles with a 500-mile range, and laboratory results are showcasing energy density targets of 400 to 500 Wh/kg. But when a company like Donut Lab claims practical solid-state deployment on electric motorcycles, are we witnessing the same revolution that giants like Toyota, QuantumScape, or KTL are pursuing? Or is this something fundamentally different? Let's deep dive into this episode today and become our first subscribers for the channel. Thank you, fellas. Traditional solid-state batteries aim to replace the flammable liquid electrolyte used in lithium-ion cells with a fully solid electrolyte, typically ceramic oxides, sulfides, or solid polymers. The ultimate goal is to pair this solid electrolyte with a lithium metal anode. While lithium metal graphite anodes used in conventional lithium-ion limit theoretical energy density to around 300 Wh/kg at the cell level. Lithium metal, by contrast, has a theoretical specific capacity of 3,860 mAh, roughly 10 times that of graphite. That is how researchers justify ambitious targets of 400-500 Wh/kg at the cell level. But what is Donut Lab actually using? Is it a fully ceramic electrolyte? A sulfide-based composite? A polymer-ceramic hybrid? And more importantly, does it use lithium metal? Or is it still fundamentally an optimized lithium-ion architecture with a semi-solid or solid-enhanced electrolyte? From an engineering perspective, this distinction is critical. A battery can use some solid components without being a pure solid-state lithium metal system. In traditional solid-state architecture, the elimination of liquid electrolyte improves thermal stability and reduces the risk of thermal runaway. However, it introduces a new problem: interface resistance. The solid-solid contact between lithium metal and ceramic electrolyte must remain perfectly stable under repeated expansion and contraction during cycling. Even microscopic gaps increase impedance dramatically. In laboratory prototypes, maintaining intimate contact often requires high stack pressure, sometimes exceeding several megapascals. That is manageable in controlled test cells, but is it practical in mass-produced automotive packs? If Donut Lab's design relies on composite polymer electrolytes combined with conventional lithium-ion anodes, it may avoid some of these interface challenges. Polymer-based solid electrolytes generally offer better mechanical flexibility and easier manufacturing compatibility with existing lithium-ion lines. However, they typically have lower ionic conductivity at room temperature compared to liquid electrolytes or sulfide ceramics. That means performance trade-offs. So how do these technologies compare directly in terms of energy density and performance laboratory? Solid-state cells with lithium metal have demonstrated energy densities above 400 Wh/kg in early-stage testing. Some companies have reported multi-layer prototypes approaching that threshold. However, these numbers often come from small-format cells under ideal conditions. Commercial lithium-ion cells today, particularly high-nickel NMC, typically operate around 200 and 5,300 Wh/kg. If Donut Lab's solid-state motorcycle battery delivers, for example, 220-260 Wh/kg at the cell level, that would be competitive with advanced lithium-ion, but not revolutionary in the lithium metal sense. Yet that might be enough for a 310 kWh motorcycle pack capable of delivering 60 to 120 miles of real-world range. The difference between 250 and 400 Wh/kg becomes far more critical when scaling to 8,100 kWh automotive packs designed for 300 to 500 miles of range, where every kilogram impacts vehicle efficiency and cost. Charging rate is another decisive factor. Lithium metal solid-state cells theoretically enable faster charging because of reduced dendrite risk under controlled conditions. Some prototypes claim 10–80% charging in under 15 minutes. But dendrite suppression remains one of the biggest unsolved issues. Lithium dendrites can still penetrate solid electrolytes, particularly sulfide types, if current density exceeds critical thresholds. In contrast, if Donut Lab uses a more conservative chemistry without lithium metal, it may achieve stable 1C or 2C charging without pushing into dangerous regimes. Cycle life also reveals differences. Lithium metal systems often struggle with long-term stability, especially beyond 801,000 cycles under automotive conditions. Conventional lithium-ion, by comparison, can exceed 2000 cycles in optimized LFP systems, for EVs expected to last 186,000 miles or more. The demands are unforgiving. Why? Then, can Donut Lab deploy on motorcycles, but not yet on cars? The answer lies in scale and risk tolerance. A motorcycle battery pack might contain tens or low hundreds of cells. An EV pack may contain thousands. Fewer cells mean fewer interfaces, fewer opportunities for dendrite formation, and easier thermal management. A 5 kWh pack has far lower stored energy than a 100 kWh automotive system. Even if a failure occurs, the consequences are more contained. Traditional solid-state developers are targeting electric cars precisely because of the enormous incentive. A 400 kg automotive battery could reduce pack weight by 30–40%, potentially increasing range by 20–30% without increasing size. That is transformative in the EV market. The energy density pressure is higher in cars because consumers expect 300 to 500 miles of range. Motorcycles, by contrast, often operate in urban environments with shorter travel distances. The performance threshold is different. From a manufacturing standpoint, the contrast becomes even sharper. Lithium metal solid-state production requires extremely low humidity environments, particularly for sulfide electrolytes, which react with moisture to produce hydrogen sulfide gas. That increases capital expenditure dramatically. Interface engineering, multi-layer stacking precision, and yield control remain major barriers, even today. Scaling beyond pilot production lines remains a challenge for most solid-state startups. Cost is ultimately decisive. Automotive battery costs today average roughly $100. $130 per kWh at pack level for large manufacturers. Solid-state lithium metal batteries are projected to initially cost significantly more, perhaps $200? $300 per kWh until mass production matures. For a 100 kWh pack, that cost gap could mean a $10,000–15,000 difference in vehicle price. So, who will win? Full solid-state lithium metal batteries may require another 5 to 10 years before achieving stable. Large-scale automotive production. Donut Lab, by contrast, may capture niche markets earlier by focusing on motorcycles and small mobility platforms. Leave a comment below and also discuss future tech. Thank you all for your support. Thank you, fellas. Before you leave, please help us reach our first channel subscribers, and don't forget to click that bell icon to quickly receive notifications about upcoming exciting content. Thank you, fellas.